Okay. So last week we talked about tensor products and we talked about natural maps. We talked about ways to look at tensor spaces as multilinear maps over your vector space and over its dual. So this meeting will continue with the application of tensor products. Um, so at the end of last meeting, we talked about why we even care about thinking of tensor products as multilinear maps, and we saw that the determinant um, gives us gives us a notion of volume in Rn. So we'd like to extend that notion into higher like vector spaces and more abstract vector spaces. Um, so so this meeting will make that connection a little stronger. Um, but before that, let me give you a rather abstract um, use of the tensor product. And we may or may not use the complexification uh, in the upcoming meetings. It depends on whether or not we get through the main portion of what I want to talk about in this DRP. So we'll see that when we talk about symplectic manifolds and classical mechanics on like arbitrary manifolds, we'll see that the complexification is very closely related to like Hamiltonian dynamics. Um, and this is sort of interesting because like the natural object then to study for physics becomes well, it shifts from real manifolds to complex manifolds. And Kähler manifolds and symplectic manifolds are very closely related. Again, we may or may not see this. So just in case we do, I think it's good to add it here. So okay. So let's start with a real vector space V. Okay, so let V be a real vector space. And what I'm gonna do is I'm gonna now define a new vector space. Okay, we're gonna call this VC. And what it's gonna be V tensor producted over the reals with the complex numbers. Okay. Um, so now this is a new real. This is a real vector space. Okay, of dimension 2 times the dimension of V, and that just follows by the fact that like tensor products make dimensions. They multiply dimensions. Okay. Why is this called the complexification though? The reason for this is we can now define a natural action of C on this vector space. So what we can do is we can take let lambda be in C, and then we define scalar multiplication by lambda, okay, to equal V tensor producted with lambda times alpha. Okay. And then we extend this linearly. Extend this linearly. And then one can check that this is now a complex vector space. Okay. So what we've done essentially is we took a real vector space and then to define a natural action of the complex numbers, all we did was we just added like an extra slot so we can just shove all the complex numbers in there and then we're very happy with that. Okay. Um now say we have this on its own isn't really too useful if linear maps don't extend to complex linear maps um, over the complexifications, and we see that it does. So say we have an R linear map. So let T be a like a linear map between B linear. And when I say linear here, I mean over R, because V and W are real vector spaces. Okay. What we can do is we can now define a natural complex linear map on the complexification as follows. So we define, um, so again, we're going to use this notation. Okay. And all it does is it takes a vector of this form and then maps it to this vector. Okay. And then we extend this linearly. Okay. Are there any questions relating to anything we've talked about? Okay. Okay. Um, but this isn't the only way to complexify a vector space. Um, we see another natural way of complexifying a vector space is by looking at what does the vector I really do, right? Like what does the number I do to real vectors, for example? So one way to see this is that the algebraic properties, so another way to define complexification. So we can take, okay, so we see I, and the main defining feature of I is that when I square it and I add one, I get zero, right? In other words, it's a root of x squared plus one. Okay. Now, naturally, vector spaces don't are not always algebras. So we can't have like we can't extend the algebra to include a vector I. So what we do is instead of looking at um, elements in V that's squared to minus one, we look at linear maps on V that's squared to one, negative one. So we define an almost complex structure J on, so J is now a linear map from V to V, linear, such that J squared plus the identity map is zero. Okay. So essentially, J will now act as I for us. And what do I mean by this? Um, I mean that we can now define a natural C action again. So if we have A plus BI times a vector V, we can call this AV plus B times JV. Okay. And now one can again check that this makes this makes V into a complex vector space. Okay. But this introduces like a limitation on introduces a limitation on the possible spaces that V can be. Um, and that's mainly because of the fact that the minimal polynomial of J is x squared plus one. Okay. Now, why is this an issue? So this is an issue for odd dimensional vector spaces because the minimal polynomial of an odd dimensional vector space, um, one can check for odd dimensional vector spaces, any linear map must have at least one real root. Okay. And the reason for this is the characteristic polynomial of linear maps over odd dimensional vector spaces is of like degree, and odd degree polynomials have at least one root. So so this construction only works for dim v is even, because this polynomial doesn't have any roots. So all the eigenvalues of J, um, all the eigenvalues of J are plus and minus I. Okay. Um, so the interesting thing is, these have just the right algebraic and geometric multiplicity so that we can decompose the complexification. Um, wait, I'm jumping ahead of myself. Um, okay, are there any questions here for what we have so far?
For even-dimensional vector spaces, I'm guessing these two constructions are equivalent, right?
Yeah, that's actually what I was just gonna get to. Um, they're not really equivalent because J the choice of J isn't canonical. Like there's many maps that give you this exact property. So it's not really equivalent per se. Because here, like when we did the complexification using the tensor product, there's only one way to do this, right? There's a canonical way of doing this. But with this almost complex structure, for example, you can check that like this is an almost complex structure on R2, because if I square this, I get negative 1, 0, 0, negative 1. But there's no reason for this number to be a minus 1, right? I could have like um minus 2, and then I could have a half down here, right? And then this also, if when I square this, I get negative 1, 0, 0, negative 1. So there's no canonical choice, and that's why I'd hesitate to say that these are equivalent. Um, but as we'll see, they're related. Um, okay. And the way they're related is if I now complexify, um, so if I now complexify this tuple into into this, now I could say that this thing is sort of canonical. Um, but again, I wouldn't really use that terminology. Okay. Yeah, so the complexification of J is now has the right multiplicities so that we can actually decompose the complexification of V into eigenspaces. Um, yeah, into eigenspaces. So we have V and V1. Okay, here V10 is the eigenspace for I, and V01 is the eigenspace for negative I. And the proof of this is actually quite simple. I think you just have to check that the map V into 1/2 um, V plus JV. Uh, I think you just have to check. Um, I think you have to check that this has eigenvalue I. Sorry, this is an eigenvector for eigenvalue I, and this is also an eigenvector for eigenvalue um, minus I. And I guess this has to be the complexification. And this sort of makes sense, I think, because again, I think like let's check this one. So if I take JC of both sides, so I can pull out the 1/2. I get JC of V plus JC squared of V. This is like 1/2 of what is it? Negative V plus JC of V. Right. So this sort of looks like if I multiplied this whole thing by I, that's sort of what I would get. Okay. Does that make sense? Okay. And as we'll see, okay, I called these I called J an almost complex structure, and um this sort of construction over here showed that like for vector spaces, almost complex structures are complex structures. Um and we'll see later on if we get there. This is not always true for manifolds. So not all always complex manifolds um are complex manifolds. Um and we'll also see that like complex manifolds are quite um like it's very hard to be a complex manifold. But once you're a complex manifold, you have quite like there's a lot of good properties that you have. Also, I made a mistake here. This should be I here, and this should be a minus I here. Yep, sorry about that. Um, and this has eigenvalue. This has eigenvalue minus I. This has eigenvalue I. And yeah, I guess you can see that from here because you have I here. Okay. So so then this becomes 1/2 J C V minus I V. But if I multiply this by minus I get this. Okay. Um, okay. Are we happy with that? Okay, I made another mistake. This should be, I had it right the first time. Okay. V minus I J C. Okay. Okay. Let's now move on from almost complex structures. Like I said again, we may or may not see them again. I hope we see them. I mean, complex manifolds are really cool. Um, but I don't know. On the problem sheet for the next couple of weeks, I will add a couple of questions as to why um, we would care about the complexification apart from looking at complex manifolds. And I mean, it's just like some cool things, and then we'll extend this idea to um, a lot of the tensor spaces that we'll see today. Okay. So now let's come back to tensor products as multilinear maps. Okay. So if we have if we have if we have T in KV or T in um, K0, then we say one, T is symmetric if sigma dot T is T. Okay. So what do I mean by this? Um, so here sigma is in the permutation group SK. Okay. And we have a natural action of sigma on on tensor spaces. Sorry, on multilinear maps. And the way we define this is that sigma dot t, and if I evaluate this at a bunch of vectors, all I do is I just permute the vectors around. Okay. So a tensor is alternating if it's invariant under the action of sigma. Okay. second. T is alternating. If it's almost invariant, but it has a magic factor of the sign of a permutation. Have you guys seen the sign of a permutation before?
The sign, yes, of a transform of a permutation, though.
Okay, so the sign of a permutation is just is the number of transpositions. It's not actually the number of transpositions. Okay, so it's one if the number of transpositions needed to get sigma to the identity is even. Okay, and it's minus one if the number of transpositions needed to get sigma to identity is odd. So what do I mean by transposition? A transposition is if I swap I and I plus one. Okay, that's what a transposition is. So say I have one, two, three, four, and I have the permutation. I don't know that maps one to two, two to one, three to three, and four to four. The number of transpositions I need to get this permutation to the identity is just one. I just need to swap these. Okay. But if I had something more complicated, like say I mapped 1 to 3, 2 to 4, 3 to 2, and 4 to 1. Um, Firstly, I don't know if you've seen this notation for permutations, but I can write this permutation as 1, 3, 2, 4. And the way you want to read this is 1 maps to 3, 3 maps to 2, 2 maps to 4, and then 4 maps to 1. Okay. So the number of transpositions I need here is, okay, let's see. So I need to swap 3 and 2, and I think that's it. No, not really. So if I swap 3 and 2, let's see. So 1, 2, 3, 4. I swap 3 and 2. Okay. So now let's look at this. Let's follow this permutation. So 1 goes to 3, goes to 2. Okay. So 1 goes to 3. Sorry, 1 goes to 2. And then 2 maps to 4 maps to 4. So 2 doesn't change. So 2 goes to 4. 3 goes to 2 goes to 3. So 3 goes to 3. And then 4 goes to 1 goes to 1. So 4 goes to 1. Okay. Um, Now if I swap, so if I, let me just write this out again. Okay, so 1 goes to 2, 2 goes to 4, 3 goes to 3, 4 goes to 1. If I swap 1 and 2, um, if I swap 1 and 2, let's see now. So 1 goes to 2 goes to 1. Okay. So 1 goes to 1. We know 3 goes to 3 because we haven't really done anything to that. 2 goes to 4 and then it still goes to 4. So 2 goes to 4 and then 4 must go to 2. Okay. If we swap, um, again, let me just write this out. So 1 goes to 1, 3 goes here, 0, here. Now we have to swap 3 and 4. So 1 goes to 1, uh, 2 goes to 3, 3 goes to 4, and then 4 goes to 2. Okay, so if we write this out, we get 1 goes to 1, 2 goes to 3, 4, 2. And then, okay, the next transposition needed is So one stays, and then you swap two and three. Two and three. So you get one goes to one, two goes to, let's see, go two goes to two, three goes to four, and then four goes to three, and then you need one final swap. Okay. So we did how many transpositions? We did one, two, three, four, five. So we did five transpositions. So the sign of this would be minus one. Okay. Does that make sense? Okay. Okay. So symmetric tensors are invariant under transpositions. Alternating tensors pick up a sign, essentially. So if I do a transposition, I pick up a sign. Okay. Now, as we talked about last time, the determinant function is alternating. Um, and so because the determinant is alternating, and we know that the determinant sort of gives you the volume of a certain area in your vector space, we see that alternating tensors are the tensors we want to assign to volumes. Okay, so we get assigned volume. Okay, so since determinant is alternating, we look mainly at alternating tensors. Okay. Okay. So now let's see what we can do with this, right? So we'd like to take a map and then we'd like to convert it into an alternating map. Does such a map exist? So we want to take a tensor. Um, we want to take some tensor. So for now, we'll look at tensors of this form, but everything we talk about will transform to like go to tensors of the other um, type as well. So we want to take a map, and then we want some map called, I don't know, alternating, so that this map is alternating. Does such a map exist? And the answer is yes. The definition is kind of cope. So what you do is you define its action on k vectors as the sum over sigma s 1 over k factorial sine of sigma, and then you just add up all the permutations. Okay. And now one can check that this is alternating. Um, I'm not gonna check it because it's quite annoying to check, but you can check that it is. Moreover, note that if t is already alternating, uh, then alt of t is just equal to t. Okay. Um, and now again, you can define this on like tensor spaces um, of the same type. Okay. You have to be a little careful when you look in mixed tensors, because in mixed tensors you swap the order of the tensor product and stuff like that, and then adding them gets a little messy. Um, so for now, we'll just stick with multilinear maps of one type. Okay. Um, and you can read the lecture notes that I'll post on Discord if you want to like see for the other types. Okay. So we call the image of alter like this map. We call it this space over. This is what we call it. Okay. This is the space of alternating um, 0K tensors. We also have this, which is the space of alternating K0 tensors. Okay.
Wait, so is alt a map from T to not from T, sorry. Yeah, is alt a map from like T to the dual of V?
Uh,
By T I mean like linear transformations on V to the dual of V.
no, so this space was the tensor product of the dual K times. So it's a map from this tensor product into
Oh,
itself.
yes, yeah, yeah. I didn't know the notation there. Sorry.
Yeah, no, no worries. Okay. So yeah, so it maps this vector. It's like an endomorphism of this vector space. Um, okay. Uh, now we now we define an operation um like synonymous to the tensor product. Um, okay, so in the problem sheet, I don't know if you guys have seen the problem sheet, but in the first problem sheet, I defined a way of looking at the tensor product um of multilinear maps. So if you haven't seen that, this might be a little confusing. Um, but you can just like remember the definition of tensor product we had before. Okay, so say we have alpha and beta in um so it doesn't okay, so let's say we have let's restrict it to this. So let's say we have alpha in this space and beta in this space. I'm not sure if we can let this be this space or not. I've never seen a definition where we allow it to be in this space, but I might be wrong. But for everything we're gonna do, we'll just look at alternating tensors and their wedge product. So what we're gonna do is we're gonna define alpha wedge beta to be k plus l factorial divided by k factorial l factorial times the alternation of alpha and beta. Okay. Um, Now this weird factor that you see up here has something to do with wanting um, the standard basis to have determinant one um, over Rn. So it's yeah, it's just that. We usually call alpha and beta so alpha, since it's in the kth alternating space, we'll call it a K form on V. Okay. So it's called a K form on V. And then beta will be an L form. We can now define the wedge algebra. So now we can define the wedge algebra as, so it's going to be the space, it's going to be the direct sum from k equals 0 to infinity of the alternate, like the space of forms. Um, but one thing to note is that this direct sum is not actually an infinite direct sum. The reason for that is you can check that the dimension of this is actually equal to n choose k. Okay. Here, n is the dimension of V. The argument for this sort of follows pigeonhole principle. So if you know the pigeonhole principle, I feel like this should be pretty easy to show. Okay. So this means that if V is finite dimensional, well, I guess we've already sort of assumed V is finite dimensional throughout all of this. So okay, I'm not really going to mention this. Um, all you need to know is that this veg algebra is firstly it's graded. By graded, I just mean it can be decomposed into like it can be decomposed like this. And it's an algebra with the wedge product. So, and it's a finite dimensional algebra. Okay. Okay, all of this is quite is quite formal and quite annoying to work with. So I think we'll do one example. But before that, I just want to mention that you should check that the wedge product isn't commutative. It's almost commutative though. You just have this factor of minus one to the alpha, minus one to the k times alpha. Okay. So it's almost commutative. Um, and then you can check that a wedge product of an odd dimensional form with itself will be zero. Again, I think that follows quite immediately from this. Okay, so let's do an example, right? Let's do an example. Let's look at the standard basis in R3. Okay, let's look at the standard basis in R3. What I'll do is I'll call the dual basis, I'll call it dx, dy, and dz. Okay, this is just a name. So what I mean by this is that dx of e 1 is 1, dx of e2 is 0, dx of e3 is also 0, and then similar for the other ones. Yeah. Um,
I mean, is there a reason why they're so suggestively named, or is that just a coincidence?
so yeah, okay, good question. So we'll see that this is a very um it's a very convenient name. Um, this has something to do. So I keep mentioning the determinant and volume. So when we talk about integration over manifolds, um, we'll see that the volume form we integrate will be just to keep with the classic notation of the integral of f dx, just to keep with this notation. So you know how you have like dx, dy, dz, something like that. Just to keep with this notation, we call this dx, dy, and dz. So instead of looking at dx, dy, dz as infinitesimals, we look at them as like something that gives you volume. And we'll see that this sort of gives you infinitesimal volume because at each point on your manifold, we assign like this dual basis to each point on your manifold in a smooth way. But yeah, we'll see that when we get there. Okay, so now let's look at what this tensor does. Okay, let's look at the action of this tensor. Um, E1, let's do E1, E2. So the best way to see this is that this is dx of E1, dy of E2 minus um, dy of E1, dx of E2. There might be a factor of 1 over 2 factorial, I think. Um, let's check. Yeah, so there is a factor of 1 over 2 factorial, but again, I don't know, it doesn't really matter too much in the grand scheme of things. So some definitions of the wedge product have the 1 over 2 like 1 over k factorial, some don't. It all depends on what you want to do. And when we do calculations, um we don't keep the factor. I'm not sure how these change. I don't think they change that much. Again, I think you could just check, see where the factors go. But I'll get back to you like on Monday. I'll let you know if it really makes a big difference. But yeah, we can see that this is just one. Yeah.
I mean, is there like a like I know this like gives me kind of like vaguely determinate E vibes, and I know that the determinant's like an alternating form as well. Is that also it's like a coincidence? Or is that like
I mean, that's
part
how
of this whole schema to build the integration up?
that's why we looked at alternating forms to begin with, right? Um, so So that's why we looked at alternating forms to begin with, because the determinant gives you the volume of a parallelogram in higher dimensions. Um, and we saw that the determinant is an alternating map. So we look at the space of alternating maps to study volumes. And we'll see that we get signed volumes. So orientation sort of matters. But okay. Yeah, and then you can check that dx wedge dy of E2, E1 is -1. So swapping the order of E1 and E2 got you a -1. Um, I might actually just get rid of this 1 over k factorial. Yeah, I think that's just better. Um, this changes by some constant. I don't know what this constant is just yet. I'll get back to you on Monday to see what that constant actually is. But this stays the same. Okay. Um, so yeah, I mean, then we can look at dx wedge dy wedge dz of E1, E2, E3. And then you can check that this actually just gives you the determinant of this matrix. So it gives you the determinant of, okay. Yeah, and then you can check that this is a diagonal matrix and it gives you one. So okay. So the
So
wedge
would that not
product,
be the identity map by how we've defined things?
this thing? Yeah,
Yeah,
it would
because
be. It would be. But you can check that like if I swap the order, then like these will swap order, and then you would no longer get the identity. You get like you get a sign.
gotcha.
Okay. So yeah, I mean like if you looked at dx wedge dy wedge dz of E1, E2, E3, you now get the determinant of the map. Sorry, I wrote the same thing. I want a 2 here, I want 1 here. So yeah, you get the determinant of let's see. So you get the determinant of, so first, and then you get a 1 here, you get 0, you get 1, you get 0, 0, 0, 0, 1. And now this is equal to -1 because you have to do like this transposition. Okay. Okay, so does this make sense? Does the wedge product make sense? Okay. So you can you can also define the wedge product taking the tensor algebra. And then quotienting out quotienting out this thing. So that should be a plus. I have a mistake in my notes. Um, yeah, so you can also just quotient this out. Basically, what this is saying is set everything of this form to be 0. So you get equals minus beta alpha. So so yeah, okay. This is another way to define the tensor algebra. Sorry, this will be the alternating algebra over the main thing. Okay. Um, okay, let's see. So now let's work in some coordinates and let's try to get a better grasp of what this means. And moreover, I want to see does how does changing coordinates, what type of map does that induce um on like these spaces? So okay. So let's take the standard, let's take some basis of Rn. Let's come back to Rn. So let's take let E1 up to En be the standard basis. And then we saw that like dx1 wedge, like all the way up to dxn applied to E1 is just 1. Okay. Now say we have a change of basis. Okay. So A is a change of basis from Rn into Rn, change um change of basis. And then it changes the basis to, I don't know, say some basis ui. So ei to ui. And now, if you recall, we know that ui has its coordinates in the ei basis given as ai. So it's this. If you remember, so you have a j there, and then you have a j here. Oops. Okay. So now let's plug this into the determinant function. So because this gets very cumbersome, I'll call this function the determinant function. Okay, it's this wedge product, like this n wedge product. So let's find the determinant of u1 up to un, and then we see that this is the determinant of ae1 all the way up to aen, and then in coordinates, this is ai1, 1, ei1, so on. And then I can factor out all because the determinant is multilinear, I can just pull everything out, like all the coefficients. So I get this. And now if you remember the definition of an alternating map, I here have a permutation. Um, so I don't quite have a permutation of the basis vectors, and that's because I might have a sum of the form E1, 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 right? So those terms are just zero, so I can just neglect those, okay, and just pretend they don't exist. Um, and if I remove all the degenerate ones, I just end up with um, a, if I remove all of them, I just end up with a permutation of 1, 2, 3 up to n. So this is a permutation in sigma, so in Sn. Okay. And if I want to re-permute everything to the identity, I just have to add I just have to multiply by the sign of the permutation. So I have the sign of the permutation. Just to be a little more explicit, I'll write this as 1 to I1 dot 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 n to IN, AI1 up to AIN n times the determinant of E1 up to En. But this is just 1. So this thing is just 1. And this thing is just the determinant of the matrix A. Okay, so this is just the determinant of A. So okay, so I mean, we didn't really do much. All we really saw is that the determinant of, like, if you do a change of basis, you just end up with the determinant. And there was nothing special about the change of basis. Um, if we just had some linear map and we applied it to the determinant function, we'd multiply the entire thing by a determinant. But now we can define something quite important. If we remember, the determinant gives us a signed volume of a parallelogram in higher dimensions, right? And if I swap two of my basis vectors, I pick up a minus sign. Well, if I swap two adjacent basis vectors, I pick up a minus sign. So it tells us that your orientation is somehow different. Okay. So what we're going to do is now we're going to define an orientation, okay, to just be like the sign of this determinant. Okay. So if the determinant of A is bigger than 0, because remember, in a change of basis, the determinant is either positive or negative. It can't be zero. So if the determinant of A is bigger than zero, we say U1 up to UN has the same orientation as E1 up to EN. Okay. And if the determinant of A is negative, then it has the opposite orientation. Okay. So what we can do is we can just pick some basis. So we can just pick some basis E1 up to EN, and just define this to be positively oriented. Okay. And this now gives you a so-called orientation on V. Okay. So this is what I mean by orientation on V. So it's just a choice of ordered basis. Okay. Um, so orientations, the so now two orientations are equivalent if the if they have the same if the sign of the determinant of the change of basis matrix is um positive. So what this does is if you look at the space of all bases, like the space of all bases, so when we talk about manifolds, this will be called the frame bundle. Um, but if you look at the collection of all frames, so when I say frame, I just mean like a basis. Okay. So it's a collection of all basis elements, not basis elements, sorry. The collection of all bases, like bases. Okay. The orientation partitions partitions into two sub-collections. And then a choice of orientation is just you pick one of these things. Okay. So the standard basis on Rn induces an orientation on R3. And then if you swap E1 and E3, the determinant of that change of basis matrix is positive. So E1, E2, E3, and E3, E2, E1 have the same orientation. Okay. But if I just swap E1 and E2, I pick up a minus sign. So I have the opposite orientation. So that's somewhat how you want to think about it. And now we can see that a choice of orientation is equivalent to a top form, to a non-zero top form.
I'm sorry, what's that?
Yeah, okay. So non-zero just means it's not zero. Form means it's in like one of these wedge product spaces. Top just means highest degree. Like k is the highest number it can be. So basically you pick omega in this space. Okay. And we see that this is equivalent because say we have some orientation like E1 up to EN is some orientation. Then E1 star wedge EN star is um so firstly this is in this space. Okay. So this is a basis. And secondly, it's non-zero. The reason it's non-zero is if I just sorry, there should be an if I just feed like this basis, I get one. Okay, so it's non-zero. Um, so on the problem sheet, I'll I'll give you some like fun exercises just to play around with the wedge product and stuff like that, so you can see like just be more comfortable with what it does. But you can just, but yeah, I mean, the whole point of the wedge product is we just want to be able to define orientations for now. Um, and we'll see that when we integrate, um, we implicitly make use of an orientation on R. And that's why when you look at the fundamental theorem of calculus, when you look at the fundamental theorem of calculus, so you have a b f prime of x dx. This equals f of b minus f of a. In some sense, this endpoint and this endpoint are oppositely oriented, right? So this sort of definition has an implicit orientation defined on it, and somehow the endpoint A is oppositely oriented to B.
But how do you make sense of this notion of orientation changing when you swap basis vectors if there aren't any basis vectors to swap?
R is a one-dimensional vector space. So all its orientations. So okay, yeah. So if one is a basis, minus one is also a base. Like if one, if you take the vector space to have basis as one, minus one is also a basis, right? For R. So
Oh yeah,
one,
I'm not doubting that. It's just like you're not able to swap any basis vectors because there's only one base
yeah.
vector.
So every map is alternating, right? Because you can only really go up to like one, so you can't really swap anything. So if you look at the definition of alternating, you're taking sigma from the permutation group of one, but the permutation group of one is just trivial.
Is it just like the identity permutation? That's it.
Yeah, there's only one permutation. So every tensor is alternating and symmetric, okay, in one dimension. Um, but orientation doesn't really depend on all like the alternating map. It says like okay, two bases have the same orientation if the change of basis map has determinant so they have the same orientation if the determinant map has orientation um like has sorry, if the change of basis map has determinant positive. So if I go from 1 to minus 1, this has determinant minus 1. So I swap orientation. And in
Oh wait
R,
up, it's negativity versus positivity. The
yeah,
notion of orientation for R.
so in R, the frame bundle is just R itself. And then it partitions it. So the frames over R, so let me just make note of this. So note, frames over R are R. So it's R cross. This is defined to be R minus 0. And now um, orientations on R partition R into two sets, and those are precisely the positive sets and the negative, like the set of positive numbers and the set of negative numbers. Okay. And the notion of orientation over here, when we talk about integration, is slightly different than when we talk about vector spaces, because in integration, we typically integrate over a surface or a manifold, and the way we define an orientation there is a choice of orientation at each point. So the idea is on the surface, you know whether you're pointing up or down, something like that. So in this case, A is sort of pointing outside the interval. So the orientation vectors point this way in AB, right? Um, but since we're going back to A, we're sort of opposing this orientation vector. Okay. And that's why
Oh
we
wait
have,
up. So is the point of the orientation vector to like make this idea of taking the area with respect to the y-axis or the x-axis, some plane, or what have you, to like make that idea more vigorous in a sense, so that you aren't taking the outside but the inside.
I mean, yeah, something like that. But again, in one dimension, orientations are sort of almost redundant because
I mean, not, yeah, obviously, like yeah, but like in higher dimensions, it's like if I want to take the integral of a sphere, it's like I want to take the inside and not the outside, and it's that with the the orientation thingamabob that you do?
So, okay, the I wouldn't go to orientations of manifolds just yet. Okay. Because again, the definition for orientation on manifolds is slightly different. Um, because again, you don't really have the notion of a basis on a manifold. I mean, sometimes you do. Like if you have a vector space, then you have the notion of a basis, and then the notion of orientation on a manifold and on a basis almost overlap. Sorry, they do overlap, but they're not the same. Um, but when you have a surface embedded in Euclidean space, you or the orientation on the surface somehow tells you if you point outward, like you have the notion of outward and inward. For example, the Mobius loop, right? The Mobius band is not orientable because if I go around one, like if I have a vector pointing upward all the time, if I go around once, I come back and I point down. Okay. So in some sense, the Mobius band is not orientable because I at each point I don't know whether like I don't know which way is up and which way is down. Okay. So
So is that what people mean when they say non-orientable manifold? It's
yeah.
the
Yeah.
notion of orientation doesn't apply to that manifold in some
Mhm.
sense.
Yeah, it doesn't. And yeah, we'll study we'll look at manifolds when we get to manifolds. But for now, the idea is just like the notion of orientations are important, even in physics. Like when you have the right-hand rule, you're picking a choice of basis, right? Um, you're picking a choice of basis, and then your cross product again, because the cross product it tells you, okay, if I have two vectors and I take the plane spanned by those vectors, the cross product tells me the unique vector that's outward pointing, outward, whatever outward is. Every vector is outward, every perpendicular vector is outward pointing. But your orientation decides whether it's pointing out or pointing in, right? So that's sort of the idea. So the wedge product, you can also think of the wedge product as generalizing the idea of the cross product. Um, and I may give you an exercise on this if you want. It's in Spivak. Um, it's in Spivak's calculus of manifolds. He gives you a generalization of the cross product um, to higher dimensional manifolds. I say not higher dimensional manifolds, higher dimensional vector spaces. Sorry. Okay. Um, it's okay. We've talked about antisymmetric vectors, sorry, antisymmetric tensors, and we've looked at an operation on them. I'll introduce the notion of symmetric tensors. Um, in a first course on differential geometry at U of T, um, you you don't really look at symmetric tensors because symmetric tensors give you um, somehow non-canonical structures like Riemannian metrics or symmetric tensors, for example. Um, so you don't really look at them that much. But I'll introduce the idea using the notion of inner products. So if we look at let V be a vector space. When I say vector space from now on, I mean real vector space. Okay. I mean, I've always meant real vector space, but specifically here, be a real vector space. Then an inner product, I'll call it G on V, is a symmetric 0 2 tensor on V. Okay. 0 2 tensor on V, that's non-degenerate. Okay. So you might have seen an inner product require you to be positive definite. Um, Unfortunately, in physics, you can't, that notion of inner product is too weak. Um, For example, special relativity, the inner product you have there is a Lorentzian inner product. Um, it's not positive definite. It's not even negative definite. It's just non-degenerate. And by non-degenerate, what I mean is, so non-degenerate, what this means is for all V in V, there exists W in V such that G of VW is non-zero. Okay. That's what I mean by non-degenerate.
Except the zero vector, I presume.
Oh yeah, every non-zero vector. Sorry. Thank you. Um, yeah, so that's what non-degenerate means. So let's do some examples. Um, so if again, I'll take whenever I say dx, right? I'm I'm in like Rn, okay, for some n. So if you look at G, you can if sorry, what did I write? Okay, if I look at on Rn, G equal dx. Oh my God. Dx1 tensor product dx1 plus dx2 tensor product dx2 plus dot dot dot. Okay, this is an inner product. Is an inner product on Rn. Moreover, it's the standard inner product, right? This is the inner product you've seen um, in university up to now. Um, in special relativity, um, we have the following inner product. We have dx0 tensor dx0 minus dx1 tensor dx1 minus dx2 tensor dx2 minus dx3 tensor dx3. So okay, as you can see, this is definitely not positive definite. But you can check that this is non-degenerate. Okay. This is sometimes called the Minkowski metric. Um, and if you note carefully, do you see the number of minus signs here? That's sometimes called the signature of the tensor. Um, so, so yeah, okay. So this is number of minus signs in an like orthonormal, whatever orthonormal. I mean, like the best orthonormal. So, and you can have vectors whose norm is -1. So that also is okay. I mean, there's nothing you can actually do about that. Um, so then the number of minus signs in an orthonormal basis is the signature. You can check that the non-degeneracy allows you to get an orthonormal basis. The process is similar to Gram-Schmidt. So non-degeneracy.
Out of curiosity, does that have to do with like the invariance? Because that kind of reminds me of that some special relativity.
Yeah, so in special relativity, we look at transformation that keep this metric invariant. Those are precisely the Lorentz transformations. So you have rotations, you have Lorentz boosts, you have spatial translations. Um, and then in Galilean relativity, we keep this metric invariant. So again, you have rotations, you have spatial translations, you have boosts by constant velocity, stuff like that.
Oh, wait up! Is that the goddamn the CT minus x minus y, no minus x square
Mhm.
minus y square minus z square thing about?
Yeah. That's exactly what this is.
Oh,
Yeah. Okay, so yeah, non-degeneracy allows you to find an orthonormal basis, similar to Gram-Schmidt. I have no idea how to spell Gram-Schmidt, so I'm just going to call it GS. Okay. Okay. So does an inner product make sense? Okay.
yeah. I am kind of curious as to why it can't be positive definite in SR though.
Um, yeah, okay. So in special relativity, if you make the inner product positive definite, you basically just get Galilean relativity back. Okay. So so usually there's a c squared factor here. I haven't put that because I put c to the um if you take the limit as c goes to zero, right? You're sort of just left with this part. So you're back to Galilean relativity. Um the the fact that the metric is not positive definite treats time and space equally, like on the same footing, but it gives you a distinction between the coordinates. Okay. And if you try to ask yourself, what transformations can I do that allow you to keep um that allow you, like if I do a transformation, I want to keep the speed of light constant. That's how you derive the Lorentz boosts. Okay. You want to keep the speed of light constant. And when you keep the speed of light constant, you see that this is any transformation that keeps that gives you that will preserve this metric or this inner product.
Yeah.
So so it's more of like so in special relativity, you want to look at more at the physical you want to look at the physical world and you want to make deductions mathematically based on that. Okay. That's why it can't be positive definite. Like the answer is just that like in special relativity, Lorentz boosts, we want to keep speed of light constant. And to keep speed of light constant, we need to keep this metric invariant.
Oh
Um,
yeah, makes sense.
I mean I can find something online to sort of show you the derivation of this if you want. I'll send it like after.
Of the space-time rule, I'm pretty sure we derived the space-time rule in 151.
Okay. Yeah, so I mean that's there's mathematically again, you just want to study the properties of these inner products. The real reason for why it looks like this mathematically is physics. And you look at the real world and you want to make deductions. Okay, so yeah, so non-degeneracy allows you to find an orthonormal basis. Non-degeneracy also gets you something extra. So you can now define a canonical isomorphism between V and its dual. And all it does is it takes a vector V and so this thing is called interior multiplication by V. And all it does is it slides V into the first coordinate. Okay. So now this is a dual vector, like this thing is now a dual vector on V. And
Is
now,
that the same as the other kind of construction you have within a product defining like bases for the dual space and all?
wait, what do you mean?
Um, because like typically like with yeah, I believe that is like the same way you get the nth coordinate basis for the dual space by using inner products instead of just like the delta.
Yeah, that it's sort of, I mean, it's a generalization of Rie's representation of finite dimensions um, to this. And this is a canonical isomorphism. Canonical. So if you remember, we talked about the fact that V and its dual are isomorphic in finite dimensions, but the isomorphism there wasn't canonical. And that's because it depended on a choice of basis. Um, Now you might argue, okay, we chose an inner product and then we got an isomorphism. But the reason it's canonical here is because you're considering V along with an inner product. So you're considering an inner product space. So an inner product space is canonically isomorphic to its dual. Yeah. You could also pick a basis and then consider the tuple of V and its basis, and that would also be canonically isomorphic to its dual. Okay. Um, Now let's define an inner product on tensor spaces. So inner product on V. But to first do this, we have to first define an inner product on the dual. Okay. So let phi and psi be in the dual of V. Then, then there exists V and W in V such that phi is equal to V and psi is equal to W. Okay. Then define um, phi psi, and this is just so this is just going to be W. Okay. This is well defined because V and W are unique. Okay. So now you can check that this defines an inner product of the same signature on the dual. So GV star has the same signature as G. This is sometimes called the I think it's called lowering the index. So this is, well, not actually this. This is called lowering the index. Like this here is called lowering the index. Okay. So let's see why it's called lowering index, okay? So let's pick a basis, pick a basis. Let's pick an orthonormal basis because we know those exist. Pick an orthonormal basis, V E1 up to En of V. And then G will have the form dx1 tensor dx1 plus dxp dxp, where now shifts from plus to minus. Um, p plus 1 tensor dxp minus dp plus 1 minus dxn tensor dxn. And here by dxi is dual to ei. Um, okay, and now let's pick v equal to vi ei. Okay, and then let's look at what happens when we push this into the thing. So consider interior product of G. So this is nothing but if I took this above thing and then I substituted in V and nothing. Okay. So if you look carefully now, this is basically just saying I put dx1 of V, dx1 plus dot 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 dxp uh, of V, dxp minus dxp plus 1 of V, dxp minus dxn V dxn, right? And this is nothing but so this is picking out the first component. Um, this is picking out the first component of uh, V. So this gives you V1. So it's so we write this as like this. Okay. So this gives you VP DXP minus VP plus 1 DXP plus 1 minus dot. Well, no, we actually write this as up because this is up. And then when we write this in Einstein summation convention, we put it down. right? But now we see that VI, so it's equal to VI if I is less than, so if I is less than or equal to P, and it's equal to minus VI if I is bigger than or equal to P. That's right, bigger than P. Okay. So in some sense, um, we've lowered the like components of the tensor. The, yeah, we've just lowered the components of a tensor. If you write this out in general, what we see is that this will actually have the form. So all the components of the of G will be lowered. Um, and then you have VI up, and then you have E. Um, yeah, so you have this. So the jth component of this thing is equal to this. Another way to write this is that this thing just equals d phi j, where phi j is a basis for v star. So in some sense, we lower the index, right? Because this is, if you look at this, this is nothing but vj. Okay. So that's why this interior multiplication is sometimes called lowering the index. Okay. Um, okay. So now that we have this, I mean, now it's straightforward um, how we define the inner product. So what we do is we let t equal so I let it equal this. So these types of tensors, I don't know if I've mentioned this before. These types of tensors are called decomposable because they're like pure tensors almost in KL. Okay. And we're gonna define and again let S be another one. Um so yeah, we have to make sure that these are the tensors of the same rank. Then we just define the inner product. I keep doing this. The inner product of T and S is nothing but the inner product of V1, W1, uh, V K, W, K, phi 1, psi 1, um, phi L, psi L. Okay, that's it. It's very simple. I mean, this is a nice inner product. Again, now the signature of G will be slightly different than the signature of V. I'll let you figure out what that signature is. Okay. So now we've defined an inner product. We've defined sort of a canonical inner product and all the tensor product spaces associated um, to V. And so this descends to inner products on the space of K forms, right? So G descends to an inner product in K form since you can just treat them as like you can just treat them as tensors. Um, and then yeah. And now comes the most profound operation on the space of forms, in my opinion. Okay. And that is to first note the following. Remember, I said that the dimension of this space, right, was n choose k, right? But n choose k is the same as n choose n minus k. Okay. Which means that the space of k forms and the space of n minus k forms are isomorphic vector spaces. Okay. A choice of inner product now makes this isomorphism um, canonical. Okay. And this is called the Hodge star. So the Hodge star is an isomorphism. So okay, technically, I guess it's the Hodge star on the kth uh all like K forms. I'm not gonna write that because I mean it doesn't really matter too much. Okay. And the way it's defined is it takes a K form alpha, maps you to Hodge star of alpha, and it has the following definition. So pick a basis, E1 up to En. So okay, I guess it's not actually a canonical isomorphism because you require a choice of orientation. But if I pick an oriented vector space, oriented inner product space, um, then this becomes a canonical isomorphism. Okay, so pick an oriented basis EI up to this one, and then define star alpha in this space so that for all beta in K forms, okay, we have that beta wedge star alpha is equal to the inner product of beta and alpha times the canonical volume form. Okay. And then alpha is the Hodge star of alpha is like well defined. Okay. So so we'll see later on once we talk about Maxwell's equations on like arbitrary space-time manifolds, excuse me, we'll see that the Hodge star is actually very important and that we need it to define two of the Maxwell's equations. Okay. So Maxwell's equations require your space to be oriented, or at least orientable. Um, and they require you to know the Hodge star. Um, let's do a quick example of like a calculation with the Hodge star just so that we're a little more familiar with the Hodge star, okay? Uh, is there any questions like are there any questions relating to this so far? Okay, gonna take that as a no. Um, okay, okay. Okay. So let's now do an example. So so let's look at R2, okay, with G equal to dx. I'll write it as dx squared. Um, and now let's try to figure out try to figure out what the Hodge star of one is. So one, um, I mean it's very clearly dx wedge dy because any if I take any number, if I take x and I multiply it by the Hodge star of one, I need the inner product of x with one. Um, I need the inner product of x with one times dx wedge dy. Uh, but this is just x. So this is the Hodge star. Let's look at the Hodge star of dx. So okay, now we take um, let's say we take dy wedge the Hodge star of dx. This should give me the inner product of dy with dx. but dx and dy are like they're an orthonormal basis, so this is 0. So the Hodge star um, of dx is plus or minus dy. Well, actually, it's like alpha times dy. And then what you can do is you can calculate dx wedge Hodge star dx is equal to dx dx wedge dy, and this is equal to dx wedge dy. But this is alpha dx wedge dy, so alpha is 1. Okay. So the Hodge star of dx is dy. And similarly, you can check that the Hodge star of dy is negative dx. Okay. Does that make sense? Are we happy with this? Okay. So I will end off like this meeting here. Um, I'll make sure that what I've like everything I've said is correct. Um, I may have made mistakes in some of the definitions. Like one of the definitions that I think I've made a mistake on is the inner product here. Um, so I'll check that. And the other one is I'll check like when I defined the wedge operation. Where did I define the wedge operation? Yeah, like when I define this wedge, I'll see what this coefficient C is. I'll see what it does to this. And then I'll let you guys know about that. So yeah, so that's it for this meeting. If there's any questions, please let me know. But I'll stop the recording for now.